All right, ladies and gentlemen, this is the second primary topic of equilibrium, calculating K from concentration. As I said in class, I've got two videos on this, one that explains the basics and goes through two examples, and the other that really goes into how we use this idea of calculating K from concentration and apply it specifically to acid-base chemistry for Ka and Kb, and also for solubility questions for KSP. It's the same concept. There are just like a few extra little things you've got to do with Ka and Kb and KSP. So I do encourage you to watch those videos as well, or at least look at the examples in the book. But first up, calculating K from concentration, our second primary topic in equilibrium. So this is an essential skill. All these questions are going to follow a similar pattern. You'll be given concentration information about reactants and products. Maybe not all of the reactants and products, but you'll be given enough. You'll be given information about concentration, not just their initial concentration, but also their final concentration. And the first thing you want to do when solving these problems is essentially figure out what you have. What are the initial concentrations that you're given? What are the equilibrium concentrations that you're given? From the information that you're given, you're going to use stoichiometry to apply changes from one thing into another. So you're going to sort of figure out what had to change for the stuff that you know based on the, like if you're given the initial concentration for A and also the equilibrium concentration for A, that means that you can figure out the change for A. You knew it had to have changed by a certain amount because you're giving its initial and final. You then, very similar to a BCA chart, you use the stoichiometric relationships, the coefficients, to take the change for the things that you know and apply it to the change for the things that you don't know. It's that whole, if you used up, if things are in a 1-to-1 molar relationship and you used up, 2 moles of the first thing, then you must have also used 2 moles of the second thing. It's very, very similar in that regard. When you know the changes for everything, you can calculate the equilibrium concentration for everything as well, right? If you know how much something changed by, you can figure out its final equilibrium concentration. And from that information, from these equilibrium concentrations, you can then calculate K using equilibrium expression. Meaning you're going to plug in your equilibrium concentrations into the equilibrium expression and solve for the value of K. All this stuff that I'm describing on this slide is essentially describing something called an ICE chart. ICE, I-C-E. It stands for initial, change, and equilibrium. And this ICE chart just became your new best friend in the entire world because you're going to be using it again and again and again when we're looking at equilibrium problems. What did it start out as? What was its change? What was its equilibrium concentration? So we're going to go through a couple examples with this. First up, reaction. H2 plus I2 goes to 2HI. What is the value of Kc if the initial concentration of H2 is 1 times 10 to the minus third molar, the initial concentration of I2 is 2 times 10 to the minus third molar, and the equilibrium concentration of Hi is 1.87 times 10 to the minus third molar? So if you look at the data that you're given molarity, molarity, molarity. You're given concentrations of the reactants and the products. It asks you for the value of K. So this is what I mean when I say calculating K from concentration. The problem supplies you concentration info, and it asks you for the value of the equilibrium constant. That's where our ICE chart comes in. And again, the ICE chart stands for initial, change, and equilibrium. And you're going to set up your ICE chart very similarly to the BCA chart that we did in acid-base titrations. Meaning, notice how the reaction is rewritten sort of below the problem. We're going to set up the ICE chart like columns for the three things. And we're going to fill in initial concentrations, changes, and equilibrium concentrations for everything. The first thing that we want to do is essentially take the numbers the problem gives us and figure out where they go in the ICE chart. Are they initial or are they equilibrium? So the first value that we have is the 1 times 10 to the minus third molar. Now that value belongs to the hydrogen, our first thing listed, our first reactant, and it says it's the initial concentration. So that's going to go here, 1 times 10 to the minus third. Notice we're using molarities. This is a distinction between the ice chart and the BCA chart, which is about moles. We are using molarities here. So 1 times 10 to the minus third molar, that's the initial concentration of the hydrogen. So then the initial concentration of the iodine, 2 times 10 to the minus third. So 2 times 10 to the minus third, that's a 3. That really is a 3. 2 times 10 to the minus third molar concentration of the I2. That's our initial concentration. And then we have one more number that we're given. The equilibrium concentration of HI is 1.87 times 10 to the minus third molar. So I'm going to fill that in on the bottom over here. So those are all the numbers that the problem has given us. And believe it or not, this is actually enough information for us to fill in the rest of the chart, to fill in the changes in the equilibrium concentrations from what we're missing. Because there's an absolutely critical number that we actually do know that is not yet in the ice chart. You can always assume, unless the problem specifically tells you otherwise, that you are not starting with any product. This problem does not tell us that we are starting with any product, which means we are going to know that our initial concentration of product is 0. The problem, we will get to questions later on where we are starting with product, but the problem will very explicitly tell you that. So if the problem says nothing at all about starting with a certain amount of product, you know that you are starting with 0, that you have nothing, no HI to begin with. Basically, we're starting with the hydrogen and the iodine, and we're letting them react to create the HI, but we don't have the HI until they do react. So we're starting at 0. Now, looking at this information, we next try to figure out change. The only one that we know for sure the change in is the last one, the HI, because we know the initial and we know the final. We know the equilibrium concentration. So then the question becomes, how do you get from 0 to 1.87 times 10 to the minus third molar? What changes that? Well, this is pretty clear. I think you've got to add 1.87 times 10 to the minus third. So that's the change then for the HI. We know we started at 0. We know we ended at 1.87 times 10 to the minus third. So in order to get there, we've got to add 1.87 times 10 to the minus third. We're going to now take that change that we figured out for the HI, and we're going to use stoichiometry to apply it to the hydrogen and the iodine. But crucial point, we add for products, meaning we're creating products. We subtract for reactants. The reactants are being used up. So while this is a plus here, it will be a minus for the reactants. We add products, we lose reactants. We use up the reactants in order to create the product. So it's a negative change for the reactants, it's a positive change for the products. So that's the difference in sign. The difference in number is coming straight from stoichiometry. HI, the change was 1.87 times 10 to the minus third molar. I'm going to do this with the T-chart first, so you can sort of see where this is coming from. We know that this is the change, but then we're going to use the molar relationships. 2 HI, I'm going to start with the hydrogen, comes from 1 H2. This is straight from the coefficients. So the change for the H2 is going to be half the 1.87 times 10 to the minus third. Half of that, because 1 H2 makes 2 moles of HI, because of these stoichiometric coefficients. It's also going to be the same change for the I2 as for the H2, because same thing. 1 mole of I2 creates 2 moles of HI. So the amount that we're seeing for the HI is doubled in comparison with the amount that was lost for the I2. So this is going to be minus 1/2 of 1.87 times 10 to the minus third. Well, at this point, we figured out what arithmetic we have to do in order to get to equilibrium concentrations. So now you're just doing math. Now you're doing what the chart tells you to do. So in order to find the equilibrium concentrations of H2 and I2, you're going to do exactly what you figured out. You're going to do 1 times 10 to the minus third for H2 minus half of 1.87 times 10 to the minus third. When you do that math, you get 6.5 times 10 to the minus fifth. You're just doing the math. 1 times 10 to the minus third minus half of 1.87 times 10 to the minus third. And then similarly for the I2, you're going to do the exact same thing. You're going to take its initial concentration, 2 times 10 to the minus third, and subtract half of 1.87 times 10 to the minus third. When you do that math, and you should, to make sure you get the same number as I do, you get 1.065 times 10 to the minus third. You have now filled in your ice chart. You always need to fill in your ice chart completely, and we've done that. That's good, but now we have to go back to what the actual question is. What is the value of Kc? Kc values are based on equilibrium concentrations, which is what we figured out in the final line of our ice chart. So what we do now is we take the equilibrium expression, which explains how the equilibrium concentrations affect the equilibrium constant, and we're going to plug in. The equilibrium expression is not some nice pretty thing that we just write and look at and admire from a distance. We actually use it. It's a mathematical formula that describes these chemical reactions. So we're going to write the equilibrium expression for this reaction. I'm going to just write it out first and then plug it. So it's products over reactants raised to their coefficients. So I'm going to do products, HI, raised to its coefficient, which is a 2, over the reactants, H2, raised to its coefficient. I will write in the 1. You don't have to, but I'm just being explicit, times I2 raised to the first. So that's the equilibrium expression. We're looking for the value of Kc. We're going to simply use all the equilibrium concentrations, and we're just going to plug right in. So the equilibrium concentration of HI is 1.87 times 10 to the minus third, and we're going to square that because of the 2. You're just literally just taking the final number that you wrote. The 2, the coefficient, comes into play by the fact that you're squaring it. That's where you're taking care of it. Then we're going to do 6 divided by 6.5 times 10 to the minus fifth times 1.065 times 10 to the minus third. It's just doing math at this point. It's just sort of plugging and chugging and going from there. When you do this out, when you do all this math out, you get a Kc value of 50.5. There are no units on Kc, no units at all. It's a relationship. It's saying that when you compare the products to reactants, products divided by reactants all raised to their coefficients, they're in a ratio of 50.5, meaning that we do have more products than we do reactants. The numerator is larger, that this equilibrium favors the product side. This is what it is. This is how it works. You fill in a nice chart and you go to the K expression. On the next slide. There are always going to be 3 basic fundamental steps to an equilibrium problem. All of them, no matter if we're doing primary topic 2, calculating K from concentration, or primary topic 3, calculating concentration from K, or if we're knee-deep in buffer problems, or if we're doing QSP versus KSP problems, there are still 3 fundamental steps that you want to do. Number 1, write a reaction unless it's given to you. If it's not given to you, then you've got to figure out what reaction is going on. This is where it's going to be maybe a neutralization reaction if it's an acid-base titration. If it's just an acid, it's acid dissociation. If it's just a base, it's base dissociation. If it's just that solid, it's a KSP dissociation reaction. But you want to write a reaction, and then you use that reaction and you fill in the ice chart as best you can. You want to make sure that that ice chart has something in every slot. From the ice chart, you write your equilibrium expression and you plug in your values from the ice chart, and then you solve. Whether you're solving for K or whether you're solving for concentration, that changes based on the problem. But it's always these 3 fundamental steps. Write a reaction, fill in an ice chart, go to the expression, and solve. That is like 99% of all equilibrium problems in a nutshell. there are application questions that sort of come from that, but that's really what you're going to be doing. So I'm going to do one more question in this video, and then the next video will be about using this process, this strategy to do Ka and KSP problems. So this question right here, the atmospheric oxidation of nitric oxide, reaction shown below, was studied at 184 degrees Celsius with initial pressures of 1 atmosphere of NO and 1 atmosphere of O2. At equilibrium, PnO2 is 0.506 atmospheres. Calculate Kp. Remember, Kp is using pressure rather than concentration, but the process is exactly the same, meaning we've got the reaction, we want to fill in an ice chart. So we look at the information that's given and fill in everything that we know. So we've got initial pressures of 1 atmosphere for the NO, so that's right here, so I'm going to write 1 atmosphere. Then we have initial pressure 1 atmosphere of O2, so the O2 is also starting at 1. And then at equilibrium, the NO2 is 0.506, so that's going to go in the equilibrium for the NO2. Now, in this case, we are using partial pressures because it's a Kp problem. Kp is based on partial pressures, not molarity. If this was Kc, we would want to figure out molarities here for our ice chart. All right, so we've filled in all the numbers that the problem gives us. Remember that we do have one additional number that the problem didn't give us that we still know, and that's the amount of starting product. No information in the question specifically told us that we started with any NO2. Therefore, we are going to know that we started with no NO2. There's no NO2 in the flask. It's just NO and O2. From this, figure out change where you can. And you figure out change where you have the most information. We have the most information about the NO2. So it must have increased by 0.506 atmospheres. That's how we get from 0 to 0.506. You add 0.506. Then we're going to take that change and apply it to the reactants using stoichiometry. Now, the NO2 and the NO are in a 1-to-1 molar relationship. It's 2 to 2, right? They each have the same coefficient. So if I added 0.506 atmospheres of NO2, I must have gotten that by subtracting 0.506 atmospheres of the NO. It's the same numeric value because their coefficients are the same. They have the same molar relationship. They're in a 1-to-1 or 2-to-2 relationship. Now remember, we're subtracting subtracting reactants. We lose reactants, we gain products. So we're subtracting on this side and we're adding on this side. And then we're going to figure out the change for the O2. But the O2 is in a 1-to-2 relationship for the NO2. So that means that its change is going to have, this is sort of based on the chi chart, right? If you've got NO2, a certain amount of NO2, then you look at the coefficients. 2 moles of NO2 create 1 mole of O2. Look at that, that's a half. 1 divided by 2. So this is going to be subtracting half of 0.506. That's the change for the O2. Then we simply do a little bit of math. It's just what's 1 time minus 0.506, and that's 0.494. And then what's 1 minus half of 0.506 is 0.747. Once you have your ice chart completely filled in, which it is now, you've put something in all possible slots, now you're going to go to your K expression. K expression, in this case it's Kp, products of our reactants raised to their coefficients. So in this case it's going to be the partial pressure of NO2 raised to its coefficient, which is a 2, so I'm going to square it, divided by the reactants. Partial pressure of NO squared times, not add, but times the partial pressure of O2 raised to the first. So that's the Kp expression, but we know numbers, so we're going to plug in actual numeric values here from that final line of the ice chart. We're only interested in what the system looks like at equilibrium. So we don't care how much we started with. We just want to use those equilibrium values. So we're going to do 0.506 atmospheres, but we're going to square it, divided by the NO, partial pressure of NO, so that's 0.494, but we're going to square that too, right, because of coefficients, and then the 0.747. then it's just doing math. It's just plugging in and solving. What's 0.506 squared divided by 0.494 squared times 0.747. When you do this math out, and you should do it as well, make sure you get the same number as I do, we get a Kp value of 1.4. Known units, it's just a relationship. It's describing the relationship between products and reactants at equilibrium. So that's how you determine the K value from concentration. And again, the second video goes into using this strategy specifically for acid-base chemistry and then for KSP chemistry as well. But it's the exact same process. It's the exact same process.